Okay. Any questions about anything?
When you are going to give us the papers,
Which papers?
the one we need to present on?
The date is specified on the website. Can you check that? I've all the details. When will I release the paper? This is specified on the website. So I don't want to say a number right now because I might say a wrong number. Okay. So just check on the website.
Yeah.
It's like, yeah, May 3 or something. But again, go and check on the website. You will have 2 weeks. So I think it's May 3 to May 17.
Okay. Thank you.
Check. Yeah. So that will be a final. There will be a homework was released this morning. Another homework will be released next Tuesday. So I know these are 2 homeworks in quick successions. I could have skipped the 6th homework. It won't be too hard. The 6th homework will be shorter. Both homeworks will have bonus points. Please try to, this is your chance to really get your grade up because I'm going to exclude your worst homework from grade concentration. So consideration. So if you do very well in 5 and 6, you could even score 130 out of 100 in each of them. So in that case, you're even making up for the midterm. So even if you did not very well in the midterm, you have a chance of still getting an A grade if you do very, very well on the homeworks and the final exam, for which you will have 2 weeks. And these details are on the website. Okay, so is Mike there? Mike Ritter?
Hi, yep.
Hi, Mike. So Mike asked a question last time about, he asked me on Slack actually, and then he posted on channel is, so let's call it Mike's question. And Meenal also asked me the message about the same thing. So Mike's question was, when we did this Zn of the unperturbed system, when we were looking at the van der Waals equation of state using perturbation theory, we did V minus NB to the power N. So we said that the molecules are made up of little hard spheres. Each hard sphere has a radius sigma. So if there was only one molecule, then this integral would have been V. If there was more than one molecule, and somehow this molecules they were not hard spheres, they could sit on top of each other, they could really go and meld with each other, then the volume would have been V to the power N if we had N molecules. But now we subtract something out to take into account that this molecule over here has this volume, this volume, this volume excluded from it, right? So what is the volume of each of these individually? That is 4 pi sigma cubed by 3. And then you have N minus 1 such hard spheres that the first sphere sees. So we are really thinking about thermodynamic limit, right? N is 10 to the power 23. So to talk about 10 to the power 23 minus 1 does not really make sense. We'll just call it 10 to the power 23. So this thing becomes 4 pi sigma cubed by 3 multiplied by N. That's why we don't have N minus 1. Then there was a subtle point, and this is what was Mike's question, is why did we do 2 pi sigma cube N by 3? This is the final thing we wrote down. Why did we divide by 2? So the idea here is a bit subtle. The idea here is that the excluded volume comes from a pair of interaction. There is no excluded volume if molecules are not interacting. Every pair of interaction leads to an excluded volume. And since we are looking at every molecule twice, we are overcounting the number of pairs. So we divide it by half. That's the rough idea. This is an approximate calculation. Essentially, all it is saying is that excluded volume is going to be less than 4 pi sigma cubed by 3n. We already know one reason why it will be less, because it's actually going to be n minus 1. And on top of that, there is some overcounting here. So we divide by 2 to account for the fact that the number of pairs each molecule shows up twice. So that's the rough idea. There is nothing profound here. The key thing to keep in mind is that it is proportional to sigma cube and proportional to n. These are the 2 things to keep in mind. Okay, great. So after that, we started talking about the new topic, and which is for the remaining few classes, which is the Ising model. So I gave you a motivation for the Ising model. The idea was that imagine that you have a bunch of little magnets that could point up, down, up, things like this. And if you bring a big external magnetic field, normally magnets align opposite to the magnetic field, right? So for this problem, indulge me and assume that when the big magnetic field is acting, let's say this corresponds to magnetic field being up, the magnets also align up. This is the way we have set the problem up, that they align with the direction of the external magnet. In reality, magnets go opposite, but I don't think this is profound. And if this magnet was pointing downwards, the small things, the small magnets would have aligned downwards. That's the idea. So, but on here we are ignoring interaction between the different magnets themselves. How are the magnets going to interact with themselves? So then we wrote down a full energy for the system, E nu, which was written as, to account for this external magnetization, we wrote it down as I is equal to 1 to n. So this is I is equal to 1, I is equal to 2, and we have n magnets, I is equal to n. And when the magnet is up, we call it +1. When the magnet is down, we call it -1. -1, +1, +1. So these are the values of the spin. So this is S1, S2, S3, S4. So we write it down as H times mu. Mu is just a unit, the magnetic moment of every magnet. If mu bothers you, you can just set it equal to 1. Your life will not change in the remaining part of this class. Multiplied by SI. This is, you can see over here, if H is positive, that is pointing upwards, then the minimum energy of this system will happen when SI is also positive for all of them, right? And the spins point upwards. So it conforms with what we wrote down. And then we introduced a second term, which was for interaction between the different little magnets. I not equal to J, Si multiplied by Sj. Here J can be positive, here J can be negative. In fact, J could go inside the summation in a general model. It could depend on which site you're at. Different magnets at different locations have their own intermagnet interactions. But we will stick with this general Hamiltonian of the system. This is the energy functional of the system, which describes how it couples to external magnetic field, how it couples to each other. So the problem that I posed last time was we focused on H is equal to 0. We turned off the external magnetic field and we look only at E nu is equal to -J, I not equal to J, Si Sj. So this is magnets talking to each other. Now, if J is positive, then the lowest energy configuration will be when all Si is equal to Fj, right? That could be +1, or all Si is equal to Fj is equal to -1. All of these will give you E nu is equal to -J multiplied by I not equal to J summation over 1. So this is the minimum energy configuration. So what does it look like? If you think about our small magnets example, the way it looks like is, imagine all the magnets are in a box. Now imagine there is a tray. It's a tray of cards or a tray of magnets that you have. And all of them will either point upwards or point downwards. We cannot tell which one will be preferred. It's degenerate. Now, imagine that you start to shake this tray, you start to shake this box, right? That is the thermal fluctuation. You give it some thermal energy. As you shake it a lot and lot and lot, these magnets will no longer be able to tell each other, stay in my direction. They will become completely disordered, right? As you increase the temperature very, very high, these magnets will look up, down, down, down. It will be completely random, right? Because the thermal fluctuation is just causing them to move. In fact, they'll be moving up and down, and then on an average, if you think about the magnetization of the system, which we define as average magnetization is equal to going to each spin and looking at the mu is the strength of every magnet, right? That's why I said it's just a unit, and the average value of that spin. This will be 0 because it can be +1, it can be -1, and they will all average out to give you a 0. So at high temperature, and this will happen even if your tray was in 2D, if your magnets were arranged in a 2D manner, Or even if instead of a tray, if you had a box where magnets were arranged along the in three-dimensional space, this would happen in 1D, in 2D, in 3D. As you increase the temperature very much, the net magnetization will go to 0. The claim that I made last time was that if you plot net magnetization, average magnetization, and I'm going to plot the modulus of this, okay? Because at 0 temperature, you can have +1 and -1, and there is a problem. Versus temperature, we know that for any system, 1D, 2D, 3D, for any system at very high temperature, the magnetization will become 0. For any system at very low temperature, at ground state, magnetization will be positive. Things will be ordered. The question is, how do they behave as a function of temperature? And the claim that I made last time, that for 1D, it drops down to 0 immediately. For any temperature, it becomes 0. Any temperature more than equal to 0, more than 0 gives you a magnetization dropping to 0. For 2D, it will behave something like this. For 3D, it will last a bit longer. So the temperature at which the magnetization becomes 0, that temperature is called critical temperature. Tc is the temperature at which M, average magnetization, becomes 0. So the claim I'm making here is in 1D, critical temperature is 0. Why do we care about this critical temperature? Because what we are looking at here, let's look at the 2D example. Until the critical temperature, we have an ordered magnet, right? Okay, the magnetic moment is not as high as you might want. For that, you have to go to 0 Kelvin, but there are strong magnets. Overall, the thing has a net magnetic moment. It is pointing in some direction. But above this critical temperature, you have a disordered magnet. There is no net magnetic moment. So what has happened is that order has changed to disorder, and the temperature at which this happens is called the critical temperature. So the claim is that in 1D, the critical temperature is 0, and as dimensionality increases, critical temperature goes up. This is the observation. This simple physical fact is what we are going to look at now using a variety of tools. First, we will look at it using an intuitive picture. So now we will understand this using intuition. This intuitive argument is also called Pearl's droplet argument. Then we will go to something called mean field theory. And then we will go to renormalization group theory, just a little bit of everything. Renormalization group theory, which will probably be the last topic of this semester. So what happens in 1D? And this intuitive picture is quite nice. You can really see what's going on. So let's proceed with it. Let's proceed with the Pearl's droplet argument. So,
Professor, just asking that critical temperature you were talking about. So, like, are they somewhat related to the Curie temperature, board temperature?
Those are all examples of Curie critical temperatures.
Critical temperature, right?
Yeah. So a critical temperature is a temperature at which a phase transition happens.
Yeah.
Okay. So all those temperatures are, because one of the nice things about this Ising model is you could represent any phase transition using an Ising model. It doesn't, magnetism is just an example, right? Any phase transition can be represented using this. You could have a molecule, bunch of molecules existing together, some in cis conformation, some in trans conformation, and you can use Ising model to map that. You call cis as 1, trans as -1, something like that. So it's a very general model, and the claim here is quite important because this is telling you that if you design a 1D material to exist in a particular ordered phase, good luck to you, because it won't stay. any amount of thermal fluctuation will kill the order in a 1D material. That's the idea. In a 1D molecule, in a 1D, if it's truly 1D, you will always have disorder. In order to have order, so that order can exist in a material, you have to go to at least 2 dimensions. That's the thing we are trying to prove. So let's look at this Pearl spelling, whatever it is. I think it changes every time, but you get the idea. Pearl's droplet argument. And I will look at this in 1D and 2D, and you will see already in 1D and 2D, it will become clear. We will not go to 3D. So in 1D, what are we looking at? We are looking at E nu is equal to minus J summation Si Sj product with J positive and H is equal to 0, no external magnetic field. And we are trying to show that for this model, there will never be an ordered phase. It will always become disordered. So how do we do that? First, let's start to talk about the ordered state with lowest internal energy. So the thing to keep in mind is that this is all internal energy. We haven't talked about entropy. And it's really it's all about calculating entropy, which will help us show what we want to show. So the ordered state with lowest internal energy will look like all spins up. That is Si is equal to +1 for all I. And note that I'm assuming these are infinitely many. Okay, n is always Avogadro number. So I don't have to worry about what happens at the edge. Otherwise, that will be an issue. So I'm always talking about n tends to infinity. Or this one, all spins pointing down, all Si is equal to -1 will have the same internal energy. Can anyone tell me what is the value of the internal energy in either of these configurations? Shams, what do you think? What is the value of E nu in the ground state? Shams, are you there? Looks like Shams fell asleep. Anyone else wants to help me?
Is it just 0?
Think about it. Will it be 0? You look at formula number 1, equation number 1.
Oh no, it'll be.
What is the value of Si multiplied by Fj in either of these ground states?
1.
Sure. Yeah.
All Si's are the same, right? Either +1 or -1. If they are +1, what is the value of Si multiplied by Sj for any I and j?
It is 1.
It is 1. Is that clear? Who was it earlier? Was it Eric?
Yep.
Who was
it?
Zoom is funny, so I cannot really see who is talking. So can you say your name? Who was it?
It was me.
Me,
I don't know if my
Eric.
voice is coming through. Eric.
Everyone is
Right.
me, so you have to tell me your name. In your frame
Right,
of reference, you're all me's. So
I
good.
couldn't tell
Does that make
if my
sense?
voice was coming through at all. Just my internet was unstable.
Yeah.
Yep.
So
That made sense.
good. So Si Fj is equal to it's always going to be +1 multiplied by +1 or -1 multiplied by +1 is equal to going to be 1. Okay, one more thing I want to correct here is I am going to look at I minus j modulus equal to 1. What does this mean? Only nearest neighbor interaction. Okay, so this spin talks to each other. So if you think about it, this is going to be E nu. I think that will help you answer the question. This is going to be E nu minus j S1 S2 plus S2 S3 plus S3 S4 plus ... and till Sn minus 1 Sn. And there are infinitely many n's, so we don't have to worry about what happens at the ends. Really, it's inconsequential. So given this, Eric, can you now tell me, since all of them are 1, right? So what is the value of this E nu in the ground state?
It looks like it should be minus j times n minus 1.
Minus j times n minus 1. And then we will use the same argument as last time, which probably Meenal does not approve of, that n is so large that there is no point in tangling n minus 1. Okay, we can keep n minus 1, but we're talking about Avogadro number of things. So this is minus nj approximately. Okay, this is the energy of the ground state. Now let's think about this is the ground state. What is the first excited state in this system that we can think of? What is the first excitement that you can cause? You have a bunch of spins. What should I do? I could topple one of them, right? I have all these. Oh, yeah, the Zoom world is a bit strange. I have no idea who is in class, who is not. So Shams, if you're back, we are talking about the ground state of the energy, which is E nu is equal to minus nj. That happened because we are thinking only about nearest neighbor interaction. Actually, even when I said that in 1D there is no phase transition, it's kind of cheating. If you have infinitely long range interactions, then you can have phase transition even in 1D, but they have to be infinitely long range. And I will discuss that a little bit. For now, we are talking only about nearest neighbor interaction. So Shams, question is coming for you. This is ground state where we said either all SIs are +1 or all SIs are -1. So E nu becomes minus j, 1 + 1 + 1 + 1 in either case, and it gives us approximately minus nj. What is the energy of this first excited state? Can you tell me, Shams? Are you there, Shams, or not? Oh, you're there. I see you now. Okay, your question.
So first excited state should be the ground state plus the energy of
The excitation. So how much is that?
it should be just J.
Are you sure? How many neighbors are affected?
2.
2. So it can't be J, right?
Right.
What was so let's mark the neighbors. This is a subtle argument. So this is the first neighbor that is affected, right? And this is the second neighbor that is affected. What was their energy before the excitement coming from these 2 neighbors? Look at the Hamiltonian. Every neighbor gives you a minus j amount of energy. So Shams, can you tell me what was the energy for neighbors before the excitement, when you had both neighbors in up direction? Here, Si is equal to Si plus 1 is equal to 1. So what is the energy here using this formula?
Minus J.
Minus j. And how many neighbors do you have?
2.
2. So minus 2j. And what did that change to after the excitement?
So
before excitation, the energy of this little thing that is affected, right? We can ignore everything else. Before excitation, it was minus 2j. And after excitation, how much is it? After excitation, you have Si is equal to minus Si plus 1. I need help. I'm stuck. Anyone else wants to answer?
It's plus 2j.
Plus 2j. So what is the difference?
Has to be like 4J. Like
4J. So this is a subtle argument. The energy of the first excitation is minus n plus 4 multiplied by J. Okay, that's the first excited state. Now let's think about increasing. So this is what we have done here, and that you can see why the name is called droplet argument. It's like you have introduced a little droplet in the problem, in the system, right? You had a bunch of spins and you introduced a little droplet. Now let's go to slightly bigger droplet. Let's think about these spins being up, 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 and then we make 2 spins as down. Okay, in this case, the ground state energy was still minus Nj, but now what is the energy of this excited state? How should we go ahead? Who wants to help me?
Would it be the same?
It will be the same. Why would it be the same, Nathan?
Oh, I mean, yeah, the 4J. Because there's like if you count the number of
number of affected pairs is always at the boundary, right? This is the key idea. Number of affected pairs. This is a simple but kind of subtle argument if you don't pay attention. Number of affected pairs is always 2. In fact, let's push it. Let's talk about an interface, a droplet, which is really, 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 really massively big. Even if it is massively big, note that internally inside this domain, these are still in the ground state because it's a doubly degenerate ground state. Nothing is affected. Only thing that has happened is to this pair and is to this pair. Therefore, E excited state is equal to minus n plus 4J for any size domain of a competing phase that appears in the middle, which means that the energy cost for excitation is equal to 4J, irrespective of how big is the, so the simplest example I can think of it is, Republican Democrat. Let's say these are all Democrats, the black ones and the blue ones are all Republicans, and it doesn't matter how many of them are flipped. It's all about the boundary. The cost only comes from the boundary. The energy cost for excitation, delta E is equal to 4J. So energetically, an excitation is never preferred, right? Because 4J is, what we're talking about. We are talking about J more than 0. Our J is positive. So energetically, excitation is never preferred. Why does it still happen? And in fact, in 1D, we are saying that it will happen at any temperature. Even if you go to any temperature more than 0, it will happen. The competing domain will form and order will not exist. So for that, we have to think about the entropy of this excitation. How do we calculate entropy? Well, if we create, let's think about in this system of spins, let's think about creating a domain like this. So actually, let's start by thinking about a domain of size 1, then it will become clear. So let's say we have to create a domain of size 1. Where can we start? We can start at the first one. Or we can start at the second one. It's a domain of only one excitation, right? Or at the third one. So there are n ways of creating domain of size 1. Okay, how about domain of size 2? What will be the number of ways of creating domain of size 2? Anyone wants to help me?
NC2.
NC2, but it's a domain of size 2, Shams. Will it be NC2 or will it be something else? Think. when you say NC2, you are saying the two spins can be separated from each other, correct?
Mm-hmm.
But I'm saying domain, meaning they are both together always.
Okay.
Then what do you think, Shams?
So it should be smaller. It should be a subset of this.
So you just think simpler. You started here. What is the next one you can do over here? You just keep moving it along. So how many ways?
N-1 ways.
N-1 ways. But how large is N? Enormous, right?
Mm-hmm.
So do I really care whether it's N-1 or N? I'm just going to call it N,
Right.
right?
Mhm.
So number of ways of creating domain of size 1 is N. Size 2 is also approximately N. Size 3 is also approximately N. It doesn't change. It starts to drop down. But if you're thinking about domains of finite size, it will stay approximately N. In an infinite, as N tends to infinity, it is always going to stay approximately N. What does this mean? This means that the number of ways of, so well, we talked about number of ways. So now we can talk about the entropy of this. What is entropy? Well, entropy is K, ln W, right? The number of ways of arranging the system. And we just showed that this is K, ln N, because W is approximately N. And if you don't, if you want to follow Sham's argument and keep into account this -1 or -2 or -3, it will be ln minus something else, but that is again K ln N, right? So this is the entropy gain. So what did we see here? We saw that delta E is equal to 4J, and this is all in 1D. This is the energy cost. While delta energy cost for domain of any size, and you can call it entropy cost, but it's basically a change in entropy that we are talking about, is K ln N, again, for domain of any size. So if you think about the free energy now, specifically the Helmholtz free energy, delta A is equal to delta E minus T delta S. What is that going to be? That is going to be 4J minus KT ln N. J is finite, a small number that is positive. In thermodynamic limit, N tends to infinity, right? Therefore, delta A tends to minus infinity. And this is why forming a domain, forming a disordered domain for any t more than 0. Let me number. This was an intuitive argument, so I wasn't really numbering everything. Let's call this equation number 2. So in equation 2, only if temperature is equal to 0 exactly, then delta A is equal to 4J is equal to positive, right? But for any t positive, howsoever small, in thermodynamic limit, 4J minus KT ln will become negative. The entropy gain will start dominating. And that's why if you plot your delta A versus temperature for the system, how is it going to look? It's going to look like this. It will be 0 at T is equal to 0, but as soon as the temperature increases, it becomes negative, which means that anytime you have an ordered state, let's say all like this, the energy, the free energy benefit of creating disorder in this system by toppling some of the spins is just so high that they will occur spontaneously. You will just end up creating pockets of disorder spins where randomly things are pointing downwards. If they were upwards, if they were downwards to begin with, they will be pointing upwards, and just chaos sets over. You end up with no magnetization. And why did this happen? Because the energy cost was so small that it did not scale with the size of the domain. It was independent of the size of the domain, while entropy benefit diverged in thermodynamic limit. So that's the argument in the pulse droplet. Is that clear?
I have a quick question about this argument.
Go ahead.
In all of this, we're saying that a domain is created. In that sense, we only have two neighbors that are going to be affected.
Mhm.
But if we split the spins across n, and as temperature increases, there are going to be more number of spins that are going to be disordered, which
Yeah.
means there would be a temperature after which delta A as such should increase. It shouldn't go to minus infinity.
Why?
Because delta S is, instead of ln n, it's going to be ln of n minus something. And
Wow.
that is going to be a large number, right?
But n minus anything is n.
Well, if we had like a really high temperature, then
Then even the prefactor here is helping you. If you go to really high temperature, you have to keep into account even this thing. So first of all, Grishma, we will look at rigorous proofs for this. The thing to keep in mind is here, I'm not really talking about this very, very high temperature limit. I'm starting in the limit of zero temperature and showing you as you keep increase the temperature, the free energy continues to go on a downward slide.
Yeah.
So it's game over. What happens at very high temperature? What happens when you start to topple more than half of the magnets? Of course, things get funky, and this argument is not the best way to use it. But I really hope that it gives you the intuitive idea for what's going on, right?
Right.
So as you increase the temperature, entropy just comes and wins over and makes it totally possible to do it. If you really start to push in this domain, this argument will get funky and we have to go to better treatments. And in fact, one of your bonus problems is that better treatment. Look at it very, very carefully, okay?
Okay.
Professor, just a question on
Okay,
that.
wait, one moment. Let me
Okay.
Is that clear, Grishma?
Yes.
Okay, thanks.
Thanks.
Yeah, Krishna, please go
So,
ahead.
so if we are thinking about toppling up to half of the spins, so after the half, should it be like a mirror image? Like it should be symmetrical after that, right?
Yeah, sure. But that's what I'm saying. Don't push our imagination to toppling more than half of the spin. When we are in thermodynamic limit, what we are showing is that creating small pockets, it will be
Okay.
downward. It will just go on and on and on. And once you start going down this domain of decreasing free energy, so this is in temperature, but you can also think of a plot where it looks like A versus number of toppled spin, right? So what we are showing here is that this thing is zero and it just discontinuously drops to minus infinity. And it doesn't matter how many have you toppled. It just goes down to minus infinity very quickly. So what you're talking about is minus 2 times infinity bigger than minus infinity or not? That type of question. But the point is, even for n is equal to 1, it goes down to minus infinity. Okay? And again, this is an intuitive argument. We will be increasing our level of rigor. So it's great that you all want to extract every last little juice of rigor out of this argument, but this is an intuitive argument, okay? And it will get more mathematical. No more math in this argument. Is your question about math in this argument? Go ahead anyway.
Yeah, this may be off topic. So I was wondering, say, when we are increasing the temperature so that it's large enough, so even in this model, we don't consider the harmonic potential. Like, will that cause some sort of melting of the whole structure?
Where did the harmonic potential come from? Where is this harmonic potential coming from? What are you talking about?
Oh, so I was talking about, say, there
Are
should be some,
Are you changing my Hamiltonian?
yeah, maybe we can change the Hamiltonian.
Well, why are you doing that? We are not talking about a changed Hamiltonian. So
Yeah, but suppose if we don't change the Hamiltonian, is there a upper limit of the temperature that we can we can take so that the Ising Hamiltonian is basically remains the same? Because I was thinking about, say, in the melted problem, when we have harmonic potentials, then when the temperature goes so high that the whole crystal structure just melts, and we won't have that sort of harmonic, Hamiltonians. So I was wondering whether that applies here.
Yeah, so most importantly, think clearly. There are two things that you're talking about. Let's not conflate them. One is whether equation number one is a good model for the problem you're trying to describe, okay? That's what you are asking. What I am solving is, given the model given by equation number one, what can we say about it, okay? So your question goes into, is equation number one even a good model for my problem?
Yeah,
That is what we are asking right now. And I don't think we can answer that question with what we are doing.
Actually, I was just wondering whether there's a high temperature limit of that model so that it remains effective.
You have to introduce additional terms. The model becomes complicated. First of all, you won't just talk about first number interactions. You will talk about higher number interactions. There will be higher order coupling, this and that. The spins themselves might not be plus minus one. It could become a Potts model. So there are gazillion of ways to generalize Ising model. Condensed matter physics is full of them, okay?
Okay, yeah. So in that case, you're saying that practically J, the coupling constant J, or some second nearest neighbor coupling constant, say J1, or some other coupling constants, they are all functions of temperature, so that
Exactly.
when we are,
you can make them temperature a function. You can start adding things, different coupling constant for second neighbors. You can make the coupling constant position dependent. Again, please listen to what I'm saying. You can make the model as complicated as possible. Which model is applicable to a problem? That's another question. Most models are not analytically solvable. Almost all models are not analytically solvable. You have to do Monte Carlo simulations or do some theory in order to solve it. This is a really, really simple model. This is so simple that it won't apply to a lot of things. The type of crystals that you're talking about, you will have to account for some external field, first of all, which is forcing the crystal to stay the way it is, right? So it becomes complicated. It's beyond not just me, but any theory to solve for the critical temperature of just generic models. It's complicated. We are not trying to do that. What we are trying to do is to take this very simple model and study its properties. This simple model is E is equal to minus J summation Si multiplied by Sj, where I minus J is restricted to only first neighbor interactions. This is the simplest model. If you made this second neighbor interaction, already our treatment will fail. It starts to become complicated. Kind of stays the same. You can look at, let's go back to the pulse droplet thing. If you made here second neighbor interaction, you can think about what happens to the number of affected pairs. If you make a third neighbor interaction, it will start to get complicated, and this argument starts to fail. But most of the things that we are going to develop here, including this mean field theory and renormalization, we are going to look at only first neighbor interactions. Okay.
Okay, yeah. So in that case, I actually want to answer like Grishma's question. So you're saying that when we're adding the second nearest neighbor or the third nearest neighbor couplings, then the increase of the entropy part will not be monotonic anymore, right? So that there might be more complicated behaviors of delta A.
So that won't come from complication due to entropy. That will come from complication due to energy.
Yeah, I see.
When you start taking, this is this term that will suddenly wake up and be like, hey, hold on. Currently, we got this free lunch that delta A is always negative because the energy cost did not depend on N. That's the simple idea here. Energy.
Oh, I see. Gotcha.
Entropy dependent. Okay, good.
Thanks.
And yeah, so this stuff is alluring because you feel like you can describe, go and read up Kitaev models and things like that. It's endless. Kitaev was my condensed matter physics teacher during grad school and stuff. They're simple models, very similar looking to this. And the solution is just impossible. You can describe topological insulators and things like that using similar models. The model becomes very complicated. So I'm just giving you a flavor of the first simplest model, which is first neighbor interactions and no external field. Good. So now well, let me remove this before people get confused and start reading Kittier model. So now let's go to 2D. What happens in 2D? Does this argument of looking at energy change versus entropy change save our life in 2D? So in 2D, let's start with a simple square lattice. In 2D already you can make things by not just looking at squares, but you could look at spins that are arranged as triangles. So some kind of, well, rotated square, if you want to think of it, right? Here the unit cell was a square, here the unit cell is like a rotated square. So you can come up with lots and lots of geometries. We are thinking only of a simple square. Now, in this, let's think about creating, we won't just have boundary. Now it's a 2D thing. So we will have a domain wall. We will have things that, let's think about the cost of creating a wall between spins of two configurations. So let's think about a wall of length L, okay? So the nomenclature is just slightly different. In the 1D argument, we thought about the size of the droplet of length L, and now we are talking about the wall, the length of the wall. So we are not talking about the number of disordered spins, but we are talking about the circumference of this thing. And it's infinite boundary condition, infinitely many of them, so we don't worry about what happens at the edge. Okay, it just goes on and on. We don't care. You could make it periodic boundary condition, which will make things a bit complicated, but we are just looking at infinite, so we don't worry about that. So let's say we have a wall of length L. I will ask you the same question. So, which means this is 1, this is 2, this is 3, and what is the energy cost of creating a wall of length L? So I'm ignoring interaction between these ones, okay? My interaction is only here, 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 and here. Only this type of interaction. This is the definition of my first number interaction. What is the delta E now for a wall of length L? If L was equal to 1, what would be delta E?
2J.
2J. If L is equal to 2, what would it be delta? What would delta G be? Delta E be?
4J.
4J. So here it scales with L. It is 2LJ. And you can see why, because this pair is affected, right? This pair went from -2 to +2. This pair went from -2 to +2. This pair went from -2 to +2. So we had, so if L is equal to 2, this number becomes 4J because -2J went to 2J. Two pairs, so let me write it down carefully. So L is equal to number of affected pairs. In ground state, every pair has energy -2J. In excited stage, no, in ground state, every pair has energy -J. In excited state, every pair has energy +J. Therefore, delta E per pair is equal to 2J. Okay, therefore, L multiplied by delta E, number of pairs multiplied by energy per pair, is equal to 2LJ. Something happened. Already, delta E is not just the boring 4J, it is proportional to L. Some sort of extensivity has showed up in it. Now let's think about delta S. This one is a bit complicated. How do we arrange this wall? In how many ways do we build the wall?
May I have a question?
Please.
So, I'm ZE. So why you are only talking about those pairs vertically, not the horizontally? So for example, between 2 and 3, there's below 2, there's a arrow that's pointing down, but above 3, there's an arrow that is pointing up, and these two, they are also the nearest neighbor, right?
Same thing. Good question. So I would call this as 3. I would call this as 4. It is still absorbed into the length of my wall.
Okay.
Okay, length of the
Yeah.
wall is it's a curved line again, and I'm using the argument that if it's long enough line, I don't have to worry about these little kinks. Okay,
Mhm.
but I call this as the length of the wall. Okay, now that I have Z, can you tell me Z? Can you help me calculate W, the number of ways of calculating how many ways can this wall be kept? Specifically Z, I want you to think about how will W compare with the following thing? 2 to the power L. Will it be equal? Will it be more? Will it be smaller? What do you think? So let's say I start here.
Yeah. So I don't understand what you're asking. So
Okay, maybe the question is too complicated. Let me write down the answer and then you all can tell me whether you like it or not. So my
Okay.
point is the number of ways of creating the wall
yeah.
will be approximately 2 multiplied by 2 multiplied by 2 multiplied by 2 L such terms. So we are here
Mhm.
and we can go, actually this is a subtle argument. Let's start with this. I want you to compare W with 4 to the power L. So 4 multiplied by 4 multiplied by 4. So I start here and now I have to make a wall. In order to make a wall, what can I do? I can go right, I can go left, I can go top, I can go bottom, right? I can move in 4 ways. That gives me a 4. So let's say I took one of these ways and I came over here. Now I can go right, I can go bottom, I can go left, I can go top. If I allowed all of these 4 ways, then I would get again another 4. Now let's say I went over here and now I think about 4 more ways. So if I allowed 4 moves at every point of the wall, I would get 4 to the power L. My question is W less than 4 to the power L or more than 4 to the power L? Is this an upper bound or a lower bound?
It should be the upper bound because
Upper bound, why?
yeah,
Why should it be upper bound?
because there's a possibility that you just if you just follow this model, at least there's a possibility that the point do not move at all,
It
which
will
means
just
that
come
there's no
back, right?
wall.
Red took you here
Yeah.
and blue brought you back
Mhm.
here and the wall disappeared. So clearly W is smaller than 4 to the power L. Also, by the same argument, you can see that W is more than 2 to the power L, right? If you just moved left to right, to right, to right, to right, if you just allow top and right, top and right, top and right at every point, right? So only top
Yeah.
or right, then clearly you're not accounting for all the moves. So W is somewhere between 2 to the power L and 4 to the power L. We are all Fields Medal deserving mathematicians. We will just say, well, let's approximate it as 3 to the power L. It's kind of in the middle, right? We have a bound on it. Let's approximate it by 3 to the power L.
Excuse me, can
Yeah.
you explain the 2 to the L again? Why do we choose that?
I want Z to help me. Z, can you explain that? Why is this correct?
So it's like it is a possibility that let's say that the wall that goes to right top and then right down. This is also possible.
Yeah.
But if it is 2 of the L, then you do not count a 1 down.
Yeah. So yeah, exactly. So I think I have the benefit of being able to draw. So I will draw here. So 2 to the power L means you go right, and then or you go top. Sorry, you go right or you go top. Now you came here again. You go right or you go top. So how about this move that you have ignored? How about this move that you have ignored? Right. So if you only account for 2 to the power L possibilities, then you have ignored some of the moves. So you have undercounted. So 4 to the power L is overcounting, 2 to the power L is undercounting. So the answer is somewhere between 2 to the power L and 4 to the power L. So we set it approximately as 3 to the power L.
I see. So in that case, we still neglecting some terms proportional to n, right? Like or to polynomials of L in front of the
Well, it could be somewhere. There are ways of even in the pulse droplet argument, you can calculate this quite precisely. I'm making a back of the envelope argument. That it's somewhere
yeah, okay,
between
cool.
4 to power L. And the most important thing is, first of all, you will see this hand waving 3 to the power L argument brings you dangerously close to Onsager's Nobel Prize winning result. So before you mock hand waving arguments, they can be wonderful. You get within like 20% of the result of Onsager's analytical result for which he got the Nobel Prize, which is mind-boggling. So let's stick with this one, okay? So 3, 4, and let's call this equation 5. So now we can calculate delta A. Let's number this page number 6, page number 7. Let's calculate delta A. That's going to be delta E minus T delta S. What is delta E? Delta E is 2JL, and T delta S is now T KB ln W. And what is W? We said, well, let's write it as 3 to the power L. It's approximately true. 2 to the power L would be under, 4 to the power L would be over. So this is 2JL minus KBT L ln 3, or L 2J minus KBT ln 3. Something happened. If KBT ln 3 is multiplied by temperature is smaller than 2J, then delta A is positive, making the wall is not favored free energetically. Or if temperature is smaller than 2J by KB ln 3, delta A is positive. And therefore, the critical temperature, and or let's write down the full thing. And similarly, if temperature is more than 2J by KB ln 3, delta A is negative, and it becomes free energetically favored to form a domain. So how do we plot this? We can plot this as delta A versus temperature. It will look linear. It will look something like this. And there is a value T is equal to TC, after which delta A is negative, and until which delta A is positive. So until T is equal to TC, it is free energetically unfavorable to create a domain wall. And after T is equal to TC, it is energetically freeable. Let me look up Onsager 2D Ising model temperature, the exact answer. I think Wikipedia has it in square lattice model. So what does this tell us? This tells us that the critical temperature is 2J by KB ln 3, right? 3 is essentially 1 plus 2. Onsager's exact answer is 2J by KB ln 1 plus square root of 2. I think this is just incredible that we get so accurate, right? If you're not impressed by this, then I'm sorry. I mean, this is very impressive. It just blows my mind away that this simple argument, just counting here and there, you know, and so basically this shows you that this 3 would have been closer if, if instead of 3, you had taken, what is square root of 2? It is 1.414. So if you had 1 plus 1.4, you could have made this more accurate by calculating the number of ways of creating the domain wall, and it actually gets even closer. But the key physical point here is that there is a temperature until which this delta A will be positive. Until that temperature, creating domain walls is not allowed. You can stay ordered. We won't take this pulse droplet argument beyond 2D. It gets complicated, but you can imagine what is the picture, right? Instead of drawing a square like this, you have to think about a cube, and you have to move on cube. And then you have to think about what is the energy cost. And there you will find that the energy cost is actually even more. So do you see physically what is going on here? In 1D cost, the energy cost is always proportional to the perimeter. In 1D cost, in 1D system, the perimeter is constant, right? Independent of how big is your domain. In 2D, the perimeter goes as the surface area. In 3D, it goes, in 2D, it goes, so in 1D, it's constant. In 2D, it goes as proportional to R, the radius. In 2D, it goes as proportional to R square, the surface area, right? In 3D, it goes as R cube. So as you increase the temperature, this is the key idea here. As you increase the temperature, delta E goes more and more, sorry, as you increase the dimensionality. So we are always thinking about delta E minus T delta S. In 1D, this was a constant. It was just 4J. It was, if you're thinking about now an abstract domain of radius R, in 1D, it was proportional to R to the power 0. In 2D, it is proportional to R to the power 1. In 3D, it is proportional to R to the power square. And this is the key idea that you can see that through this argument, the temperature at which the delta A becomes negative, that temperature itself increases. The temperature until which you can sustain positive delta A goes up. In 1D, it was 0. So this is the Pearl's droplet argument. It's really intuitive. It's really hand-waving. Many of you pointed out things we could do better, but I still think it's quite beautiful and just shows the power of how hand-waving arguments can get you to such wonderful results. Next thing, we are going to do mean field theory, which has also won prizes in many forms and it's used all the time. Mean field theory is a disaster in 1D. In 1D, mean field theory gives you a critical temperature which is non-zero. It tells you that you can have ordered phases existing in spite of thermal fluctuation, which is completely wrong. However, mean field theory gets more and more accurate as you go to higher dimensions. The key idea behind mean field theory is every spin looks at an averaged behavior of all other spins. What do the other spins look at? They also look at the average behavior of all other spins. And how do you calculate this average behavior? You set up a recursive relation in order to calculate this average behavior because, and we will work through all of that. So that's the next thing we are going to look at, which will be mathematically a bit harder than what we just did, but it's nice ideas and it's useful. And then finally, we'll go to renormalization group theory, which allows us to kind of coarse grain our perspective. It says, instead of looking at one spin at a time, why don't you look at 2 spins at a time? Why don't you look at 4 spins at a time? And how do you expect the properties of the system to not change, whether you're looking at 1 spin at a time, 2 spin at a time, 4 spin at a time? So Onsager won the Nobel Prize for his work for calculating basically this thing, apart from other things. You don't win it for just one result. And later for renormalization group theory, Leo Kardanoff, who was at Chicago, he did not win the Nobel Prize. Actually, it went to Wilson. But the 3 people who really worked on this were Ken Wilson, Kardanoff, and our own chemistry's Michael Fisher. These are the people who worked on renormalization group theory in the 60s and 70s. And we will look at some of those ideas also. So I will try to post a more detailed proof of this Pearl's droplet argument on Slack. If I forget by tonight, please remind me in a direct message or in general, I will do that. So these arguments that I just mentioned, you will see them in a better typewritten manner. And yeah, so I don't want to start mean field theory today. So I just want to stop here. Any questions about this? So, and as you think of questions, one thing I really want to point out is today we have a super exciting seminar at 1:15 p.m. by Andrew Ballard, who is Ballard, I don't know. He's a scientist at DeepMind, Google DeepMind. He's a chemical physics PhD from UMD. So many of you are chemical physics students. And he works at DeepMind on a variety of things. And today his talk is about free energy perturbation, which you studied. And he, in fact, cites Zwanzig's paper in his abstract, the paper that I suggested. And he connects that to machine learning and AI. So if you can come, the link is, I posted it on the Slack channel. It's at 1:15 p.m. today, so please try to attend. It will be useful. And the homework is out. this is the last long homework. I promise sixth homework won't be that long. I know you have other things happening. Basically, I'm trying to help you improve your grades. So please work hard on this homework. Don't ask for extensions for this one because it will make my life complicated. It will make your life complicated. It will leave even less time for homework 6. So do the best you can. If there is a medical reason, of course, I'm happy to give an extension. And the final will have papers for you to read from. I have already been posted papers. At least 1 or 2 of them will be on the menu. There will be other papers. So the Zwanzig's paper or Feynman's paper, something like that. It could be Chandler's paper on how to map a quantum system into a classical system. And if you have any papers that you want to read, please send me in direct message. If you make a case that why that paper should be included in the final exam, I'm happy to consider it. So if there is a paper you want to include, please share with me. No questions?
Not related to this, but about the lecture. So I cannot attend. I have office hours, but these lectures are recorded, right?
I think so.
So I can, in principle, request you for the recording, right?
It's all on YouTube. You haven't been to my YouTube channel?
Oh, okay.
Oh, no.
So just a question.
I thought you are all going to make me YouTube influencer. It's not gonna happen. You don't even know about it. Oh no, it's all on the website. You never go to my
Okay.
website, is it so?
Okay. I do go for seeing the homeworks.
Every single video is on YouTube.
Okay. Yeah. So that means from the last year also videos are there, right?
I guess so, half of them. But why do you want to
Okay.
go to that? I don't think I did a better job last year or a worse job. I think I did equally excellent job last year. But you can if you want.
Yeah, there was that talk on AI and thermodynamics from a Google guy. I just wanted to revisit that.
Well, that talk is today.
There was a talk last year also.
Oh, maybe it's possible.
Yeah.
It's possible. Yeah, I forget. Time moves. It's been a long year, as you all know.
Yeah. Okay.
Good.
Okay.
So I will post the first Doppler argument. Please go through it. These are important concepts. The way we are looking at mean field theory, especially, is an important concept. So I cannot really make. If I make hard problems on them, they will become very hard. These are all intuitive things. These are advanced part of the semester. Try to get the gist of what's going on. And please ask me questions on Slack. Not all of you have received full participation points. The best way to get them is to ask questions. I'm happy to give full participation points to everyone. As some of you have already been participating, but please ask me questions on Slack. Don't be shy in asking on general channel because it leads to more discussion. No one is judging you, and just ask questions on general channel or in direct message. Okay, so see you on Thursday. There's a chat message. Yeah, there was some seminar. Yeah, anyway.